data types, data structure, data algorithms. These are the things we're doing. So basically it consists of data types, arrays and strings, representing numbers, binary arithmetic, hex, converting binary numbers, float point, bitwise manipulation, and character sets. So these will be explained using paint and then done. So first of all, data types. Each pair of data that is stored has a type. This determines what you can actually do with it. For example, integers, whole numbers, what you can do is addition, multiplication, etc. But you can't use it like for strings. Whereas strings, well, characters are single letters. They have an ASCII value, and these are stuff such as A, 1, Z, etc. Next is strings, I think. Okay, Boolean. These are true or false. So these can be either one of two things. They can be true. So say you had something where you were asking for the age. If the age is more than 15 or less than 15. If it's more than 15, it'll be true. Less than 15, false. Simple. Float and real numbers. These in Java would be known as doubles, and they would be decimal point numbers. Any number which has a decimal. So Boolean, character, string, integer, and float and or double. Can we use double? No, it doesn't count here, but it'd be float. These are any numbers which have decimal points attached. Which would be the most appropriate type to store a username? A username would be a string. This is because it is a string or multiple characters. Casting. Casting is a process of converting data from one type to another. One of the main reasons for casting would be output. Outputs must be formatted as strings. Well, yeah. So you may need to convert certain things such as Boolean into strings. All inputs also come as strings that must be converted from two other data types. And casting functions, so str3 gives 3 as a string. Int 3.4 gives 3 because obviously 0.4 can't be a integer. And casting to a float can be done using float functions to float, and then the speech marks mean there is a string that's converted to a float. Right, we're back. All outputs must be formatted as a float, and all inputs will be inputted as a string. No, it must be formatted as a float, as a string, and all inputs will be input as a string. What is one of the most common reasons for casting? It would be input and output. So every piece of data that is stored has a something. This determines how it is something and what you can do with the data. So every piece of data that is stored has a type. This determines how it is stored and what you can do with it. Some examples. Complete this code snippet. X equals 3. Print str. And that stands for string. So print the string 3. New Zealand, USA, Yellowstone. This is there on the map. Well, that's quite close, you know, for just not knowing where it is. Next, arrays and strings. Cool. Arrays are really useful when you have lots of related data that you don't want to store in multiple variables. Arrays. An array is a data structure that stores a fixed number of values under a string identifier. The values must be the same type. So for example, you have an array, and the array is called what you should do to this video, and it has the curly brackets, and the value should be like, comment, sub. And obviously in arrays this value is 0 and this value would be 2 because it starts that's a 2, yeah, because it starts counting at 0. Right, array elements, I've just said this, it starts at 0, and arrays in pseudocode. An array of 10 items can be created using the following syntax. Array name of array 10. Values can be assigned. So name of array 0 equals hello. So in the first place, or the 0th in this case, it would print hello. And if you were to print that position in the array, it would print out hello. Simple. So the code snippet here would be something my array 10, my array 0, hello. So what you would do here is you would make sure that you put in the word array, and that defines the array. I actually didn't know what you had to do, so I paused it to check out different answers to make it seem like it worked, but I didn't. So times relating to array, a data structure that stores a fixed number of values under a single identifier, that is an array. A piece of data inside an array, Jesus, give us a second. So the single element would be called an element, because elements inside an array, and the index is the position. So 2D arrays. A 2D array is a data structure which consists of an array of arrays. So a 2D array is a data structure where arrays are filled with other arrays. This can be used to represent 2D surfaces or I get it. To access an individual array, we can use the array as usual. My array equals my 2D array 4. But to access an individual element, you use this syntax 5.0, which would get the first element of the 6th array. I will draw this out for you in a second. So 2D arrays. 2D arrays are often used to represent 2D surfaces, for example a chessboard. Each element of the 2D array could contain the chess piece that has a location. 2D arrays can be used to represent a database. The outer array is a collection of records. Inner array stores a single record. Okay then. So if I were to organize this as a chessboard, this would be, for example, inside the array, blah blah blah, blah blah blah. So as a chessboard, it would be 1, 2. Let's just have 3 in here. Well, we're not doing it as a chessboard. That takes too much, and like a basic explanation would suffice in this case. 4, 5, 6, and then I feel like we need one more just to be able to get the overall full aesthetic of this. 7, 8, 9. So basically, here we have 3 arrays. So the first thing you would do in my array, sure, it would be to call which array you want. So this is array 0, this is array 1, this is array 2. So you would call array, say you wanted this one, the middle one, you would call array 1. And then you would call what position you want within. So this is 0, this is 1, this is 2. So say you wanted position 2, that'd be it. Simple. So complete the code snippet. My element, my 2D array, 0, something, and then select the first element of the 6th array. So that'd be 0, because obviously it starts counting backwards. So 2D arrays could be represented something and something arrays. So something array could represent a record. That's a normal array, I guess. Well, this one's a 2D array. Single and multiple? Single? What? Can be used to represent a record? I've been looking at this and I have no clue. Because obviously here, this doesn't exactly help us. Oh, wow. Outer and inner array. So, can be used to represent a record is the inner array, and can be used to represent a collection, outer array. I explained that. Because the inner array would be yar, yar, yar. Those parts of the inner array, so this array, while the outer array is the whole thing. That took too long. So, strings. Strings are special cases of arrays or lists, where each element is a character. there are many methods we can apply them. So concatenation. Concatenation is joining two strings together. So hello plus world. Concatenation. Accessing a character. So say if you have a string, you can very easily access a character in that string by using, well, this in the pseudocode, but there are multiple other ways in every other programming language. For example, get char. So a length string, you can just use len, get length, etc., and it would give you the length of the string. And substrings, a substring is a part of a longer string. In pseudocode, you can write substring.substring start position number of characters. So this takes a substring starting at start position characters of first and takes the stated number of characters. So I thought that it just double clicked. So it looks at the string and it only takes the first however many characters are there. So what is concatenation? That's adding two strings together. So complete this code snippet to output world. My string hello, comma, world. New string equals my string substring. It can only be numbers really. Oh yeah, it starts with this. So 1, 2, 3, 4, 5, 6, 7, 8. It's not 8. My string, output string. So it's start position and then number of characters. So start position is at 0. So not. The start position is, this is 0, 1, 2, 3, 4, 5, 6, 7. Start position is 7, and the number of characters is 1, 2, 3, 4, 5. Simple. It took a while. We are learning. How do we access the first element of an array? My array, 0, because it starts counting at 0, obviously. A something array is a data structure where arrays are filled with other something. So a 2D array is filled with other arrays. You needed the S. Wow. I get it. So, string operations. Concatenation. Well, length is one of them. What else can you do with them? So you can check the length. You can get positions. Well, you can get certain parts of substring. Substring. Yeah. There's four things on there, obviously, so that was one of the 4. That one took a long time, you know. The first one didn't take nearly as long. So, binary. In everyday life, we use the denary number system, so that is 1, 2, 3, 4, blah, blah, blah. Computers use binary instead. Binary is sets of 1s and 0s, so I will summarize this because I actually know what's going on here. Well, in me, we've been doing this. So binary is either 0 or 1. If there's a 0, that means there is nothing there. Well, if there's 1, that means that there is something there. So in this case, binary would be 2, 1, 2, 4, 8, 16, etc., etc. So, to represent the denary number 17, well, what two numbers add together from here to give 17? 16 and 1, and the rest would be zeros. Simple binary, done. So we've done that. And hexadecimal. So hexadecimal is basically splitting this up into groups of 4. So 1, 2, 3. Now it's groups of 4. So as far as hex goes, the system goes, it goes 1 to 9, then 10 is represented by A, and 15 is represented by F. So in this case, this and this would be 1, 1 in hex. Simple. And hex is just so less characters are used and less human error. Which of these are true about hexadecimal versus binary? Hex is easier to read. Hex can't be stored digitally, and hex is shorter. Simple. We're not going to watch the video. This is the video. Sign and magnitude. So, I can actually explain this. So, sign is the absolute first number, which represents if it's a positive or negative number. So, for example, here, the sign plus or minus that, and then the magnitude could be here. And the magnitude, let's just say it's that. So, per se, here was a 1. That would mean that this would be 1, 2, 4, 8, 16. So if this was a 1 here, that would mean it would be minus this value. So that would be a minus 16. Then it would be plus 8, because 8 is here. Plus 4, because 4 is obviously here. Plus 1. So that would be 13 minus, that would be minus 3. Whereas if this was a 0, this would just be 8 plus 4 plus 1. So that would be 13. So that's sign and magnitude. Simple fact. So, what character do we set the MSB equal if the number is positive? Number is positive, we set to 0. The following number is written in notation. What is its denary value? So this is a 1, that's a 2, 4, 8, 16, 32, 32 plus 1, 33, quick maths. So convert 11 from denary to binary. That's just easy, isn't it? So, starting with the largest power of 2, they'll fit into 11, 8, leaving 3 left over. So our first digit is 1. Try the next smallest power of 2. 4 will not split into 3, so our next digit is 2. 1. I don't actually know what this is trying to do. I'm so confused. Like, what do you mean? This is not how it... What? Start with the largest power of 2. That's split in, so that's 8, leaving 3 over. So our first digit is 1. And then it's 0. Oh, as in this is doing it manually, but that makes it so much more effort. But surely you just do that. Simple. Like if you're doing A-level computing, you should know this. The following number is written in sign and magnitude. What is its denary value? So that's 1 plus 2 plus 1 plus 2 plus 8 plus, not 16 plus 32 is 43. Easy. So convert 10101 from binary to denary. So the first place has a value of 1, so that is 1, 2, 4, 8, 16. I could have probably done that a lot quicker. That's 4, and that's 1, so that's 21. Easy. So, this is going to be a long video. This is going to be like 40 minutes, you know. Fair enough, I'll take it. Binary addition. We can take two binary numbers in the... Okay, screw this. I am explaining this my way. Like, I'm not relearning this. If I know how to do it, I will just teach it. So, binary numbers. 0, 0, 0, 0. Add 1, 1, 1, 1. 1, 0, 1, 0. Add 1, 1, 1, 1. And 1, 1, 1, 1, add 1, 1, 1, 1. These three should be able to teach you the basics. Actually, no. We also have 0, 0, 0, 0, and 0, 0, 0, 0. So there are multiple ways of doing binary addition. First of which, you can just convert these into denary, and that's add. So that would be 0 plus 15, which is 15. But obviously that is also really boring, so... And you won't get any marks for it. So in this case, 0 plus 1 gives 1. 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 Lovely. This one, 0 plus 1 gives 1. Now when there's a 1 and a 1, it gives 0 and you carry a 1. 0, 1, 1, 2 1s, 0, carry the 1. When there's 3 1s, it becomes 11. Now, 1 1 becomes 0, carry a 1. 1 1 1 becomes 1, carry a 1. 1 1 1 becomes 1, carry a 1. 1 1 1 becomes 1, carry a 1. These are what are known as overflow errors. That means that there are too many bits for the amount of bits available. You don't care about those unless you get a 4 marker on them. And these, 0 add 0 is 0. Simple. I don't think we need to go over this anymore. You know, so what is overflow? When the number is too small to be stored, nope. When you have digits which are not 1 and 0, nope. Too many empty bits, nope. When the number is too large, yeah. When adding two ones, we must carry 1 and place a 0. Simple. So binary shift, once again, I can do this, so we are not using that, we are using my own mental abilities. So, binary shifts. Say you had the number 0, 1, 1, 0. So that is the number, the hell was that? That's the number 6. So, if you were to binary shift one place to the left, so going that way, all the values would just move one place this way. So that would be 1, 1, 0, 0, thus making it 12. So every time you binary shift left, it's a times by 2, while say you were to have a binary shift one place in the right direction, from this one obviously, not that one there, that would be 0, 0, 1, 1, which would be a divide by 2, which would equal 3. This is the same for every time you go another place left, it times is by 2, and every time you go another place right, it divides by 2. So that's all we need to know. I can check if I missed anything. Nope, nope. So a binary something is a technique for performing multiplication or division. A binary shift. Simple. I just didn't click anything. Okay, we're doing it anyway. How can a number be multiplied by 8? So that is 2 times 2 times 2. 2, 4, 8, which is 3. Perform binary addition. 0, 1, 1, 1, 0, 1. So here is 1 and 1. So that makes... I'm looking at the wrong thing. So that's 0, carry the 1. 0, 0, 1 is 1. Simple. So what are the results on 2 left shifts on this? That means all the values would go left twice. So that would mean that this would move 1, 2 here. Then there'd be a 0. Then there'd be 2 1s. So 2 1s would be that. Simple. Simple, easy, fun. Hexadecimal, that's next. Okay, hexadecimal numbers. Hexadecimal is a fast and easy way for humans to process rather than binary. So, I will do this here instead of on there because I also know this. So, hex uses 16 different things. These 16 things are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then are A, B, C, D, E, F. So A represents 10, B 11, all the way up to 15. So, as we have these 16 and we have all of these, what happens is each binary, 4-bit binary, can go from 0 to this, which is 15. So, in this case, that 0 to 15 could be represented by one of these values. So obviously 0 being 0 and so on and so forth all the way up to the 15. So, if you were to look at, say, the number F7, you would know that that would be the binary value 1111 1111 0 1 1 1. So obviously the value F7 is a lot easier to look at than all of this and a lot easier to process, but you know exactly what it looks like instead of having to actually like count it all out, etc. So it's just easier for humans to be able to understand. Disadvantages: computers can't obviously process this, so that's a problem. So which of these are valid? There are 3 of them. Not this one. This one is valid. This one is valid. And 9A is valid. 9A is literally 9 and then 10. C14 is it 13? Or 12? It's 12. 12 and then 4, and F5 is 15 and then 5. Hexadecimal is used extensively in programming languages such as machine code and pseudocode, programming languages such as that, and what else? Assembly languages, which like require a lot of human interaction. Oh no. Using hex. Hexadecimal is used for HTML to display colors. So kind of like ASCII, it is literally ASCII. Each thing has a different value, a different hash value, and in some cases those would be represented as hex. So for example, when you were coding HTML, you would have seen the color hashtag FFFF, and that would obviously be hex. That was a terrible attempt at that. So in HTML, colors are defined from how much they are red, blue, and green on a scale of 0 to 255. 0 to 255 are the range of numbers that can be represented in a single byte. One byte is 8 bits, obviously. So this means you can use two hexadecimal digits to be able to represent each byte. Simple. So HTML color codes start with a hash symbol followed by 3 hexadecimal numbers, such as that, obviously. So now we can see that HTML colors can be broken down into this. So the 00 FF00, so the FF obviously stands for 1515, and in this case the 00 is a red value, which is 0 units for red. The FF is a green value, and the 00 is a blue value. So obviously, although there are like 3 sets, it doesn't mean that it's like a massively long number. It is literally 2 sets of binary. And MAC address. A MAC address is a number that is uniquely identifies a network device. The MAC address is made up of 14 bits, which are shown as 6 groups of 2 hexadecimal digits. I think that's pretty simple to understand. The first 6 hex digits show the manufacturer, so who made the device, and the next 6 will show the serial number of the device, thus your uniqueness. A MAC address is made up of 48 bits, which are shown as 6 groups of 2 hexadecimal digits. So RGB colors, we've just been through this one. There are 16,777,216 colors that can be specified. That's a bit mad, you know. Which of these are true of hexadecimal versus binary? So hexes are a lot shorter, easier to read, and are used in debugging. What's the maximum denary value that can be represented by 2 hex digits? 255. Which of the following gives the manufacturer of the device, so it's the first 6. So 1, 2, 3, 4, 5, 6. So 6A, BB, 17. Easy. Too easy. So we are halfway there, and it's been half an hour. The next 1, 2, 3, 4, 5 should be easier. Converting binary and hexadecimal. Both binary and hexadecimal can be used to represent the same number, so it's important to be able to convert between them. Yeah, simple. How to convert between, we just did this. Converting that from binary to hex, so split it into 4 groups from the right. So that is 0010, so convert the first group. Well, that's okay. I would prefer it to have another 0 on it, but okay. That's 1 and 4, so that's 5. Is it not? Oh, I'm an idiot. 6. That one is 8 plus 2, 10, 11, so that is A, B. Convert the third group, 2. Put the digits together, 6, B2. Simple. So what is the binary number, blah blah blah, in hexadecimal? So that is obviously 8 plus 4, which is 12. 12 is, A would be 10, B would be 11, C would be 12. Simple. Converting denary and hexadecimal. Both denary and hexadecimal can be used to represent the same number, so it's important to be able to convert between them. Denary to hexadecimal. The easiest method to convert denary numbers to hexadecimal is, oh, we don't care, we know how to do this, is literally just like take the number, convert it into binary. Okay, I'll do one example just because you asked nicely. So 16, convert it into binary. Convert it into binary. And then convert that into hexadecimal. 10. Simple. So convert 24 from hexadecimal to denary. So work out the powers of 16 above the digits. The hell? What do you mean work out the powers of 16 above the digits? Okay, sure that. So multiply the digits by the power above them. 16 times 2 equals 32. Add the values together. 36. The easiest method to convert denary numbers to hexadecimal is to first convert the denary into binary, and then convert the result into hexadecimal. So convert that number from binary to hex. So first 4 bits from the right. So the right is obviously this side. So that is split into groups of 4. Simple. So convert the first group, which is that. So that would be 1. Convert the next group, 8, 9. So 19. Simple. Converting from hexadecimal to denary. So first of all, for each column, multiply the hexadecimal digit by the power of 16 above it. Okay, this makes no sense. Like, that's obviously the answer, but that is not how I would do it. Honestly, that is like one of the stupidest methods of doing it. Floating point and binary. Oh, you're gonna love this. Floating point. A floating point binary number is made out of 2 points. The mantissa and the exponent. Ready? So I'll explain this one. So basically, we obviously use standard form to be able to represent. Wait a second, to be able to represent numbers such as, sure, this number with a lot of zeros could be represented as 10 to the power of 8. Yes? But the problem would be that in some cases in binary, this would also be something that people would want to do. So, in this case, so, say we have this. This was a pretty big number, obviously. This is 255.5. So, this would be represented in float point numbers as this point moving 1, 2, 3, 4, 5, 6, 7, 8. So, that'd be 0.1111111100. So, this would be the mantissa. And then there's an exponent, and the exponent would be 8. That is obviously because to be able to get this back to its original number, you'd have to move the full stop or the decimal point back 8 places. Simple. So that is literally what float point numbers are. So, yeah. So, convert the following number from float point into decimal. So, I will show you the other way around using this. So, the mantissa is obviously 1001010. Oh, so you've done that, yeah? So that'd be 100101. So that's the mantissa, and that's the exponent. Obviously, in the real thing, they would give you that this is the exponent instead of just letting you decide. Determined where the binary point moves. So, is 0. The binary should move how many places to the right? It should move. This number here is 5, so it should move 5 points. Considering the exponent is 5. So we move this 5 points. So 100101. Does that move 5? 1, 2, 3, 4, 5. That'd be 0, so that'd be point. Yeah. And then that's obviously the new exponent. And convert the mantissa into denary. So this would be 0.5, 2, and 16. So 0.5, 2, and 16. So that is 18.5. Simple. So float point is a method of representing numbers in binary, which makes use of a binary point after the most significant bit. Normalization of float points The same decimal number can be represented in a number of different ways using a float point, depending on the bits available. To ensure the mantissa is as precise as possible normalized, the binary point and exponent should be adjusted so a positive number has a 0 before the binary point and a 1 after it, and a negative number should have a 1 before binary point and a 0 after it. So normalization is basically the simplest form of writing it. So for example here, this number would not be normalized. Normalization would be this point becoming here. And in this case, this is the normalized format. And this would not be normalized because of this not being a 0 and this is a negative number. So normalize the following 12-bit binary float. So identify the mantissa and the exponent. So 1.1010001. There we go, that's the mantissa, and the exponent is obviously that, so that's 4. In decimal, wait a second, 1, 2, 4. There's 4, is it not? Wait, 1, 2, 3, 4, 5, 6, 7, 8. That is there, so that's 4. Remembering the... There's no way you're asking for a quarter. Yeah. Well, there's no way it's anything else. Convert the exponent into decimal. 4. It's 4. Wait a second. This exponent? But it's completely different here. You're sending me mixed messages here, man. The exponent is 12. 8 plus 4. That's 12. I can do this all day. What the hell do you mean? What? Fuck off. But... Okay. Move decimal point between the different bits in the mantissa. So that would be 1. Wait, that would be 0.0001101. Oh, nope. That would be 1101.0001. Nope. I'm having a nightmare here. So convert exponent and decimal this, and move the decimal point between bits in mantissa. This isn't normalized anyway because it literally says you have to make sure that that's like that. Is it that? No. What is it? How have you got 11 then? Where's 11 come from? Change exponent. The decimal point has moved. Let me guess. 1 place to the right. The exponent changed from -4 to -5. New thing is that. So combine the mantissa and the exponent on the answer. Wow. To form answer. Well, that's the mantissa. And where's the exponent? 1101. Do you mean is 11.0100011101? Okay, that was a bit of a nightmare. But we move, sure. Which of the following 12-bit floating points are unnormalized? So which of these are not normalized? So this one's normalized, this one's normalized, this one is not, this one is not. Simple. What are the two components of a floating point? So, mantissa and exponent. Why wouldn't you just let me type 2? A positive number has a 0 before the binary point and a 1 after it. That's to make it normalized. So convert the following decimal point, floating point decimal to decimal. So the mantissa 0.011101, and the exponent is that. So the exponent is 9. Determine where the floating point moves. It moves 9. MSB, determine where the floating point moves. 1. Y, the binary point should move to the left is 0. This is not how you do it. No? So remember to change exponent to 0 to 0. So we have literally just like moved this by 9. That's what you've done. Don't know what you're trying to do here. Point no 1 1 1 or 1 1. So they're going backwards instead of forwards. Why? 1 times 2 to the minus 2 is 0.25. 1 times 2 to the minus that is 0.165. Is it not? 1 over 8. 0.125. And this one would be 0.0625. Yeah, then the answer would be 0.25 plus 0.125 plus 0.0625, which would be 0.4375. Yes, it would be. So the next part, floating point arithmetic. So this is addition using floating point. So the basic premise is, continuing with just on floating point, is when you add them, you need to make sure that the exponents are equal. That's it. That's all you need to know about. It's simple addition, but you need to make sure that the exponents are equal. So compute the following addition, that plus that. So obviously the exponent here is 2, and exponent here is 1. So change the exponent of the first number. So exponent decimal 2 to 1. So move the binary point in the mantissa. The exponent is decreased by 1. So the binary point has moved 1 place right because it's gone down by 1. So now we add these. So this is 0 0 0 1 0. Carry the 1 1 1 0 point. Oh my god. 0.01. Yeah, that just took effort. So then we normalize it. So because there's a positive number. Wait, why have we done that? I thought it was a positive number. But they've kind of like fully got rid of the rules. So they 0 1 0. That's what they've done. So the answer with exponent is apparently that. Beautiful. So what are the steps? Match the exponent, combine the addition, and then normalize the result. Very simple. So subtraction. In binary subtraction, what you do is basically when you add two numbers, so say 7. Now when you subtract two numbers, minus 5, what you are doing is you're basically doing 7 plus minus 5. So what you do in binary subtraction is you find the negative of that value and you use that. Simple. So compute the following floating point subtractions, that and that. So the exponent here is obviously 5 and the exponent here is 4. So you make that from 4 to 5. And then you move the binary point in the mantissa. The exponent is increased by 1. So the binary point moves 1 place to the right, to the left. If it increases by 1, does it move to the left? Sure. First 2 complement. So that is change all the values around and add 1. So that is 1.0001111. Then obviously you add another, and then you add 1. So that is that, is it not? Is that not 2's complement of it? So it's 0.111, and then it's 4 zeros. 1 2 3 4. So we're trying to find 2 complement of this. So that is 1.0001111. 0 0 0 1 1 1 1. Then you change the first number, you add 1. So there's 2.0001111. Is that not it? 1 minus, then 1 over, give us a second to figure this out. Okay, so it turns out literally, what? But, oh, I think they converted it back and then they did it. So if we were to add this, it'd be 0 0 1 1 1 0 0, I think 0 0, and then 1 1 0 0 0 point, yeah, sure. Normalize that, so now it'd be 0.110. Then the answer with exponent would be 0.1112345010. Simple. So that was how to subtract. The first step to subtracting floating point numbers is to match the exponent. Compute the following addition, that plus that. So change the exponent of the first number. The exponent decimal goes from 4, 5, 2, 4. No, that's 3, idiot. So the exponent is decreased by 2. The binary moves 2 places left. Why does it not? Why? Because if it's moved, because it's moved from 3 to 5, that means that it's got closer. Which way is moving? Right is moving that way, moving from that to there. So the mantissa would move from that to, oh, it moves 2 places right now, so there's that 0 0 1 0 1 0. Yeah, it's not apparently. So is it this? 1 0 1 0. Oh look, it's moved to the left, so I was right. So 0 1 0 0 1 1 0.0. I'm not annoyed at all, as you can see in my voice. Normalize this now, so you times. Oh, let me guess, you go right again, don't you? Yeah, why wouldn't you go right? And the answer would be simple, BAP. The first digit of 2's complement corresponds to something in decimal. First digit of the 2's complement corresponds to the sign. Factor this in when you do the addition. Sign in decimal. What does it correspond to in decimal? It corresponds to the sign. Does not? Mine, yes, a sign. The first digit can be a 0. So change the exponent, that to that, so it goes from 1 to 2. The exponent is increased by 1, so the binary moves 2 places. So let me guess, left even though it moves right, you autist. Stupid thing. So what's happened here then? Oh, you've just decided that you're actually going to move it to the right direction. You're actually going to move it left this time instead of right. So finds 2 complement of the second mantissa. Oh, how about this? Yeah? Why is it that then? An answer with exponent 1.12345678. An exponent 0010. Happy? No? Too many zeros? And let me just add zeros until you give me the answer. Wow. Stupid website. Garbage game. I'm doing physics after this and hopefully doing better. Bitwise multiplication. So shifts. Bitwise multiplication is the order of modifying data by changing the bits within individual bytes. Logical shift right. A logical shift right moves each of the bits in a byte one place right. The least significant bit, so the absolute last one, is lost. And the most significant bit is filled with a 0. So that's the same as a shift. And the same is done in this one. A rhythmic shift is almost the same, except the most significant bit is a sign bit and always remains the same. In an arithmetic shift has the following results. This goes into this, so the first number remains constant. And in this one, as it goes left, it goes from this to this, so this number always stays constant. And circular shift is when, say you had this, and then you were doing a shift this way, it would then become bap, 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 and then 1, and then this in step 3 would move to the front again, thus becoming 1, 0, 1, 1, 1. Simple. So logical shift, right moves each of the bits in a byte one place to the right. If you're telling me I'm wrong, though, I will throw something at you. So, what is this? Arithmetic shift right. Why is there arrows here? Arithmetic shift right, so right is going this way, so that one, sure. Screw this. Doesn't matter. Bitwise multiplication masks. So, okay, I actually do know what this is. So, say you had the values. Let's just do 1, 2, 4, 8, 16, 32, and you were to do this, what you would do is you would, and say the question was asking, you want to change the 8th value to a 0 without changing anything else. What you would do is you would do the value, you would do this 0, 0, 1, 0, 0, 0. Then you would use XOR and you would get this 1, 1, 0, 1, 1, 1, and that would be masking. So which type of operation set digit equal to 1 for bits corresponding to the 1 in the mask, or leaves them unchanged? What type of operation? Masking. Oh, addition. Is it not addition? It's binary addition, is it not? For example, what? Or, well, XOR is what I used. What's the result of the following? So, this would be 0, 0, 0, 0, 0, 1, 0, 0, so 0, 0, 1, 0, 0, 0, 0. And then, where's a logical shift left? A logical shift left. A logical shift left. So left is going that way. It's that one. That's pointing right. What like the hell is this? It's pointing right. Perform an arithmetic left shift on this one. So arithmetic means the first digit is sustained. Because it's going left, it's going this way. So that is this one. I'm pretty sure. Yes. Yes, now. And the OR operator sets digits equal to 1 for bits corresponding to the 1s in the mask, or leaves them unchanged for bits corresponding to the 0s in the mask. And thank God for that, we're done. Jesus, thanks for watching, peace.